this program together. It's so diverse and it's so stimulating and exciting to see very different ideas from different fields. So I will bring a different field now, which is of free fermionic systems. And actually, I would like to change the title of the event, of this talk, to a series of fortunate events. And I hope it will become clear why I changed the title to that. Actually, it's not a change of title, it's just an alternative title. Okay, so the outline of the talk, I will give a motivation to try to study free fermionic systems. And then I will introduce a model that we are going to consider in this talk, but the method is more general. Then I will tell you how to obtain the mass gap of this model, and then I have to introduce a polynomial. So it's just the root of a polynomial. And then there will be 3 fortunate events to obtain this polynomial. Then I will tell you the method for computing the root of this polynomial, and there come 4 more fortunate events. And then I will apply this method to 3 systems, and then comes the 8th fortunate event. So it's concatenate things. It's amazing that everything pays out in the very end. It requires a little bit of faith, but it worked. So why to study free fermionic systems? Well, it gives you exact and reliable results, so it's good to have them. And then you can use it to benchmark other methods that would work in other non-integrable systems or interacting systems. It can give us new insights because you can, since they are more, let's say, between quotations, easy to understand, you can understand other phenomena. And it can also be used as a test bed of new ideas. So if you think that a new phenomena can be described by free fermionic systems, you can use it. And then you can generalize it to other more complicated systems. And the second motivation is that free fermionic systems, well, they do exhibit interesting complex behavior as quantum phase transitions, fractionalization. We have seen that here in this conference. It has localization and Griffith singularities and many other interesting phenomena. So, okay, what's a free fermionic systems? Well, from the undergrad stat mech, it's a guess, right, of fermions. We can, after managing or after some algebra, you can put that in this quadratic form in fermionic operators, which anti-commute. And the quasi-energies of this fermionic system do not depend on the occupation, on how many electrons or fermions you put there. So the energy of the system is just the sum of this quasi-energy if there are or there is not a fermion there. So you can manipulate it, and you can write down a diagram like this, where you have the plus epsilon 1 minus epsilon 1 plus epsilon 2 minus epsilon 2, and then you have to put 1 fermion in each circle. So the Pauli principle is just is equivalent to put 1 particle per circle. It's just a way to write it, and it's convenient for later on. Okay, so that's a free fermionic system. So I'll introduce the model that I'm going to work here. This model is the following. It has density energy, Hamiltonian. So lambda I is some coupling constant. and HI is an operator, a set of operators, which equals to identity when they are powered to n. And n is a parameter, integer parameter, 1, 2, 3. And the peculiarity of these operators is that if they are close to each other, they obey this algebra, where omega is the root of 1, the nth root of 1, exponential I 2 pi over n. And if they are far apart, larger than p is another parameter of the model, so I have two parameters, n and p, they commute. So that's the model. It's somewhat pretty general in some sense. And let's see what this model describes. For instance, if n equal 2 and p equal 1, this is the transverse field is in chain. That's I wrote here. So the odd lambdas are the transverse field, and the even lambdas are the coupling constants. So you can see that this guy anti-commute with that and this one, but commute if this far apart, larger than 2, distance 2. So the conventional solution is a mapping to free fermions via Jordan-Wigner transformation, and here's the Jordan-Wigner transformation, and you translate these spin operators into fermionic operators, and the eigenenergies are those that is written here. Just like last slide, right? So the quasi-energies are the eigenvalues of a L by L matrix, so where L is the system size, or proportional to the system size. And it is known from long ago, since 61, by Lee Matschultz. All right. When n equal 2 and p equal 2, this is Fendley model. Unfortunately, he left. I would thank him for putting this model forward. It has some flavor of free fermion of the easy model, but it's very different, actually. And you can see again that this operator anti-commutes with the 2 on the left and 2 on the right, but commute with all the rest of the operators. And the solution, amazingly, there is no Wigner-Jordan transformation for that. So you would say, okay, then this may be an interacting system, but it's not. Well, I cannot say that precisely because what is a non-interacting system and the interacting system may need a review of this concept. There is a free fermionic spectrum for this system, and the roots the quasi-energies are the roots of a polynomial, but there is no Wigner-Jordan transformation. We know the energetics, but we know nothing about the wave functions. Yes. Yes, just like this one here. You put a fermion there or not. But if you want S to be different from 0 or 1 or plus or minus 1, then we go to n equal 3 and p equal 1, the Baxter chain. So this is the Baxter chain for n equal 3. So x and z, they can be represented by this matrix. So this is a model that's non-Hermitian. There is no Wigner-Jordan transformation for that. However, there is a free parafermionic spectrum. And again, this quasi-energies comes from a root of a polynomial. In the case of a lambda equal 1, these roots are known. It's just cosine to the power 2 over n. So you can get imaginary quasi-energies. But the Pauli principle here for the parafermions is generalized to the circle exclusion as before, but you can only put one particle per circle. So this is somewhat a generalization of the fermion to parafermions. You can think about, can be interpreted like that. And S now can be 0, 1, or 2. Yeah, this is non-emission, so if you think of some time evolution, there will be non-unitary. But I will not talk much more about parafermions here. So if you allow me to introduce one more model, then you can have some generalization of that Fennelly model, which you have xy here and a product of z's. And how many z's you put here depends on this value of p. And they obey this algebra. And x to the power n minus 1 is this conjugate, and it's the same for z. And they have this structure that I was telling you. Just do the math, and it's easy to see that. And again, there is no J-finger transformation, but we know the eigenvalues, all the quasi-energies, and then you can construct it from this rule here. You can put S as whatever you want between 0 and n minus 1. All right. So this is the model, completely generic, and let's see how do I get this so-called polynomial, right? Because everything seems to be around this guy. Okay, so the polynomial. The first fortunate event is to find an active number of conservative charges in evolution. I don't say that it's simple to see that, but this slide gives you a flavor. How is that? The first conservative charge is the Hamiltonian. So you sum the density of energy densities only. The second one is a product of these energy densities, but they have to be far apart, larger than p. So if they are far apart, larger than p, it's somewhat easy to see that they commute with Q1 or commute with H. And this is involution. So you can keep doing this line of thoughts, and the LF charge, conservative charge, is just multiplying these energies. But these guys here, these energies, they have always to be far apart, larger than p. So you can, after some hard work, you can see that they are all in involution and they all commute with each other, so they are conservative charges. All right, and then you can write this generating function for the charge, which is this guy here. All right, so the second fortunate event, it bears magic. It's the inversion formula. So if you get n equal 2, for instance, and you get that generative function and multiply it by the same function but with argument minus u, all that operators, they become proportional to the identity times a number, which is the polynomial that I'm talking about. So that's somewhat magic, but you can generalize for all n's. For generic n, you just get to multiply these many generating functions and you get identity. Okay, and since it's a polynomial of u, you can show that this is a constant times u to the power n minus the roots u to the power n. All right, so that's the second fortunate event. The third one, No, no, it's not. It's a fortunate event, right? It's not obvious at all. But if you do the math, you can show this. You have to sit down, and after I don't know, a couple of hours, you convince yourself that's it. Oh no, there is another fortunate event coming on. We have to wait. Okay, so that's the polynomial, right? The generic n, for instance. And let's see what happens if I act this series of products of generating functions on an eigenstate of the Hamiltonian. So remember that these G's are sums of the charges. So the first charge, remember, is the Hamiltonian. So here's the first charge, the Hamiltonian to the power n. And of course, the next one is the first charge times the second charge, and so on. But it's a different power of u. Here you have a u to 2 to the n plus 1, and so on. And since it is the Hamiltonian is an eigenstate, you get an energy to the power n. So that's the left-hand side of this formula. So let's go to the right-hand side of this formula. You can show that this constant of this polynomial is 1. So what comes to the right is 1 minus u over the root of the polynomial to the power n. And then you have to do this product. And the first term is u to the n times the sum of the inverse of the roots to the power n. So since it's a polynomial, you have to match all the powers. And then we see that the energy to the power n is just the sum of the roots of this polynomial to the power n minus n. And then you have to solve this equation here, which everybody in this room knows what is this. It's just that. No, I'm kidding. You don't have to know. This is highly non-trivial. But after some day of working out and putting the computer, and then you see that's the solution of this equation. En equal to this sum here. That's the solution. Where S can be anything between 0 and n minus 1. Well, but if you look at that, you can identify the quasi-energy as being the root of those polynomials to the power minus 1 over n. So that's the polynomial. You find the roots, put to the power minus 1 over n, and then you fill up your Fermi C or whatever state you want. All right. Yes, that's a parameter of the Hamiltonian, right? I'm saying that these operators obey this algebra, and that's. No. Well, omega can be somewhat encoded in this algebra here, but not explicitly on omega. Remember omega, if I put omega plus omega square plus omega cube or until to the power n, I get 1, because it sums to 1. So that's why this is part of the magic that I was telling you, that this is just proportional to identity, because the omega goes away. All right. Could you repeat, please? The this is the, you have to solve the polynomial. That's the next step. I did not solve it yet. I know that as a polynomial, it has to have roots. And I'm just in this slide here identifying the roots with the quasi-energy. I'm not saying that so far, I'm not saying that this Hamiltonian here is a free fermionic from Hamiltonian, but I found it, the energies of this Hamiltonian, and I can identify it as a free fermionic spectrum. No, I'm not assuming anything so far. The U's turn out to be real for this model here. But then when you get the square root of this thing here and put omega, it's fading away. Since omega is complex, then you can have energies that are not real, but the polynomial is real. All right, so how can you use the polynomial to compute the mass gap, right? The polynomial is written in a generic form in this here. And that's the fourth fortunate event that I can generate this polynomial recursively. I put one more operator in the system, and coming from that, it's not easy to see that, but when you compute those conservative charges, you can see how the next conservative charge depends on the previous ones. They do not depend, but how many of them appear, they lead us to conclude that the polynomial depends on the previous polynomials in this fashion here. It's not easy to see that, but believe me, the math was done carefully. So I compute the polynomial for L equal 1, and I feed that to this recursive formula, the recurrency formula, and I get the second one, and so on and so forth. So this gives us a computational time of order L square. If these lambdas, these couplings are all uniform, like let's say 1, I can compute these coefficients analytically. It's just a factorial. So these coefficients go factorially fast with L. So you get a polynomial with coefficients that are huge. Well, they are not so huge here because I'm still 6. But if I go to 100, then you get something that is of order 100 factorial and so on. It's not easy to deal with this polynomial numerically, because you cannot store these coefficients in the machine. Because if you go to 10 to 100, you get a exponential of 100, and you cannot store that in your computer. Actually, you can, but it's useless to manipulate it, because the first one is 1. So you get 1 and another one that's exponential to 100, and you are doomed to numerical instabilities because you don't have the precision anymore. So what's the polynomial good for? And in homogeneous systems, how do you compute it? Well, I know the recursive, but the polynomial will be messy, and I don't know much of their coefficients. So what's good for? So comes the fifth fortunate event, and somewhat the hero of this talk, which is Mr. Laguerre. The same Laguerre of the polynomials. So a long time ago, I have never seen the Laguerre picture, so I put here, I got it from Wikipedia, and I got this picture from there. So this is Ms. Laguerre, right? We know the face of Dirac, Schrödinger, but well, now you know the face of Laguerre. So Mr. Laguerre, a long time ago, he put forward this theorem that if you get this polynomial, the largest root, I'm calling U max, is smaller than this ULB, which is Laguerre bound, stands for Laguerre bound. And Well, it's not a nasty formula, it's a simple formula. You have to forget about this bar here, it's just L. And you see that it involves only three coefficients, the three last coefficients, CLL and L minus 1 and L minus 2. So you get a polynomial, and you imagine how this theorem, you get only three coefficients, the last coefficients, and you say that all roots are smaller than whatever it is. This is an amazing theorem. Most of theorems put bounds to the roots. They involve practically all coefficients. But Ms. Laguerre found a bound that involves only three coefficients. So this is promising because I don't need all the coefficients of that polynomial, I just need three of them. And three of them, they are not so far apart, so numerical stability will not be an issue. So these three last coefficients are easy to compute, but then you can say, okay, you know the bound, you know some of the coefficients, and what for? What's useful? Or when it's useful, if useful. And then comes the sixth fortunate event, that you have to realize that the gap, the mass gap, is proportional to the minimum quasi-energy, which is proportional to the maximum of the root of the polynomial. And the gap of a gapless, the finite size gap of a gapless system vanishes as L2 minus Z, where Z is the dynamical exponent. So if you are looking for a gapless system, we know that we are interested in critical exponents, then you get one critical exponent here from this method. But why this is it, right? You have to see that the largest root become widely separate for large L. Why is that? Because the system is gapless. So this E minimal tends to 0, U max tends to infinite. So if one root is shooting very far from the other roots, you just need to expand your polynomial around that root, because all the other ones are far away. You get by Taylor expansion, you get a simple line or parabola, and that's it. That will be enough to find your root, the maximum root. So I don't need the entire coefficients. I need just a bunch of coefficients near the last coefficients. So I don't need the entire polynomial. So I have just to compute the last coefficients of the polynomial, and the computational time that's of order L. And the third thing is that the method works better for critical systems. And that this is complementary to methods that are available in the literature. Usually, what we do, we get our Hamiltonian, put in a matrix, diagonalize it, and if the correlation length is small, you get the mass gap for small system size accurately. But when you go to some critical point, this correlation length diverges, and then you need a larger and larger system size, and you are doomed. But here's the other way around. If the system is gapless, then I need very few coefficients to compute this mass gap. And this works of computational time of order L. No. No. Oh, well, they are real. They have to be real. Yeah. But that's right, because what we get from the recurrency relation is that these coefficients depend on the coupling constants, which are all real. So everything will be real here. All right, so that's the summary of the method. We can compute the polynomial recursively, keeping only, you need only to keep 15, 20 coefficients. We went up to 30 because we were very careful to be sure that we are not doing anything wrong. And this computational time is over order L. Then you compute the Laguerre bound. And we use the Laguerre bound as the starting point of Newton's method to find the largest root. And once you find the largest root, you can compute the mass gap. And you do that for different system size. You can compute by brute force the critical exponent, for instance. Sorry? For CFTs is 1, if your theory is CFT. But if it's not, then it'll be something else. And I will show you that. Okay, that's the method. So let's do some application. And let's see, for instance, for clean systems. So you can look at, for instance, the Fennelly model. So that's the Fennelly model in his paper from 2019. And he found the 3 gapful phases and the phase transitions and a multi-critical point. These phase transitions are in the easy universality class. So if you apply the method here in these red lines, you get z equal 1. But if you apply the method in this multi-critical green point, you get z 3/2, which is not CFT. But nonetheless has this free fermionic spectrum. We apply the method for that. For instance, you go up to 10 to the 7, which is in 1D practically is practically microscopic, right? 10 to 23 divided by 3 is of this order. So I do different system size, right, up to there. And I compute this gap and also the Laguerre bound. So the Laguerre bound are the dashed lines, and the true mass gap is the continuous line. And you can barely see a difference between them. There is a tiny difference if you zoom in, but I'm not doing that here. But the most important thing is the slope of this line here is the dynamical exponent. And you get 1.5 with 0, 0, 0, 0, many zeros, with a high precision. And it took only 10 seconds in my laptop. So you can see numerically, you verify numerically that the Laguerre bound can give us z that is equal to the true z. And the Laguerre bound, remember, I need to compute only 3 coefficients. And I have the analytics for those 3 coefficients. I can work that out. And analytically, the Laguerre bound coming from the dynamic exponent coming from the Laguerre bound is p plus 1 over n, analytically. So that's the 8th fortunate event. The Laguerre bound, so Miss Laguerre gives us a bound, and the root is shooting to the infinite, and Laguerre bound is going to the infinite in the same way. So that's very fortunate, right? It doesn't have to be, but it happened. Luckily, that's the case. All right, so let's apply now for random systems, which I think is when this method is most useful. Because there are very few methods for random systems. Sometimes few theories are not applicable to random systems, and random systems lacks lots of methods to tackle them. Okay, compared to clean systems. So just to have a flavor of what's the physics of the random transverse field is in chain, it's well known. you get random couplings, and for instance, you can put a uniform transverse field, but it could be random as well. But when the fields are all bigger than the couplings, you are in a gapful phase. So blue is spectral gap. You are in a gapful phase, a gapful paramagnetic phase, which is a conventional paramagnetic phase. If all the fields are smaller than the J's, you are in the ferromagnetic phase where there will be a spontaneous symmetry breaking in the thermodynamic limit, and also a gapful phase. So it's a conventional ferromagnet. Things start to be interesting when the transverse field goes very close to the typical value of the couplings, because now, although in the great majority the fields are greater than the couplings, it's still a paramagnet, but it's a gapless paramagnet. And this gapless paramagnet has finite correlation length, but system is gapless. And this is called the Griffiths phase. So we understand why it's gapless here is because there is a chance that you find in the middle of your system a rare region where all local couplings here are bigger than the H, so they are rare because this probability of having J larger than H is this tiny area here. So I have to flip the coin many times and get the same thing. So this is exponentially rare. But this rare region here is locally ferromagnet. But if it's locally ferromagnet, it becomes locally a super paramagnet with very slow dynamics. Because to flip all these rare regions, you have to flip them coherently because J is stronger than the fields here. You cannot nucleate a domain wall. You have to flip them coherently, and this time is exponentially large. So you have exponentially large time means that it has exponentially small gap. So this fills up the gap of the bulk. So all the low energy physics comes from these rare regions. Yes. You do have, even if it's infinite support or finite support, doesn't matter. I can show you that. You just need a rare region, right? Yeah, that's no problem at all. Still, yeah, you can put a box here. Imagine this is a box. So there are these. Let's say the box is like this, right? So you have this tiny area where J's are bigger than the. No, if you are outside the box, then you are back to this, yeah, to this. Yeah. Yes, correct. Yes. Because the critical point happens when the field reaches the typical value of the J. That's the quantum critical point here, where magnetization starts. All right. So that's just to give you a flavor of the physics that's coming out, right? Because I'm going to apply the method. What I do in this graph here? I compute that polynomial for different system size, compute the Laguerre bound and the maximum root, and with that I can compute the gap. So this gamma here is log of the gap, right? And we expect that this goes as z log z. And they do go to z log z, as we see here. There's not a much big system size. I can go way further. There's no need to do that here. And I did that inside that Griffiths paramagnet phase in different points. So black one is this one, and red one that, and so on. So you can see that the z changes as you go close to the quantum critical point. So z is changing inside the Griffiths phase. And again, we see that the Z coming from the Laguerre bound. I compute the open symbols are the true mass gap, and the crosses are the Laguerre bound, so they match. So Z equals ZLB again. And that's what we get from analyzing the systems in the Griffiths paramagnetic phase. If you go very close to the quantum critical point, the Z diverges, it becomes very big, and lots of finite size effects happen. And there is something that we do not understand. If I put a surface field here, when there is no surface field, there is lots of finite size correction. So it vanishes as 1 over L, log correction. But if I put a surface field, this finite size correction vanishes much faster, exponentially faster. So I'm very happy with this result, but I don't understand that, and this is not understood in the literature. We found that numerically. So applying this method and the transverse field Ising chain, which was done many years ago by Daniel Fisher, that got practically all results. There is still results that are not known. This is very large chains, spin chains, 10 to the 7. All right. So if I scan the Griffiths phase towards the critical point, I can compute this dynamical exponent Z, and it diverges. And this dotted line here is analytical prediction, which comes from the solution of this equation. And for Z very large, this is proportional to 1 over 2 delta is linear. This divergence is a linear in log scales. And this distance from criticality is the difference between the typical value of H and J. So this analytics, it was known since 95 and 2001, and our numerics fit very well on it. The different, only the magnetization. If you put, the correlations are the same, the Z is the same in both sides, only in the susceptibility, sorry. Because there is no magnetization in the paramagnet, there is a finite magnetization in the ferromagnet, okay, that's a difference. But the susceptibility is different. But Z is the same, correlation is the same. Correlation function and correlation length. Oh yeah, but then the red region is a little bit more tricky. The red region is the following. You get let's come back here, right? Unfortunately, I don't have the graph, but suppose that this bar here is right here. So the bulk is ferromagnet, right? But there are some regions where H is larger than the J's. So this is a paramagnet region. And it can be arbitrarily large. And inside this paramagnet region can have a rare region, which is disconnected from the bulk, almost disconnected from the bulk, and is fluctuating very slowly. And this kills the gap. So it is there. It took a while to people to realize that, but now it's well known. So the critical point, we go there. Z is infinite, right? We are seeing a theory. Probably most of people never heard about a theory that has dynamical exponent infinite. So how is the dynamics actually? So this gamma log of delta is diverse as a power law of L to some power, and turns out this power is universal, 1/2. Doesn't matter if you use box distribution, binomial distribution, Gaussian distribution, this 1/2 is universal. This is order independent. And we see that. So we compute here the distribution of these gaps, and we divide by L to this power. So this should be, for different size, this should collapse into the same curve, and it does. So this is an analytical prediction, and the red lines are our numerics, and doesn't fit well because the analytic prediction is not exact. It's just an approximation. But it is a good approximation because it's very close to the exact result. And this is just for again, to say that this computational time is of order L. So I diagonalize the system size that goes up to 10 to the 5 in this graph here. And I compute the computational time for doing this using this strong disorder RG. That's something very simplified to do. So it's hard to beat it, but it's proportional to L. So the Laguerre bound is also proportional to L, and the exact is also proportional to L. And see the system size, it doesn't take even a second to do that. All right. So let's go to my final application, which is to Fendley's random model. Then I put random couplings in these phases. And that's what happened with this model. It becomes very rich when you put randomness. If you put randomness everywhere, let's go to panel B, what do you get? All those easy universality class transitions, they become infinite randomness transitions. So this order is relevant. And they are surrounded by gapless Griffiths phase, just like in the easy model that I just showed you. And this multicritical point is also in the psi 1/2 infinite randomness multicritical point. So when you put randomness everywhere, it's just like in the easing case, more or less. But if you put randomness only one of the couplings, let's say lambda A, then it's much richer. This transition between BN and CA is the same as in the random easing case, but the transition between C and B is different. If you are if lambda A is very small, which is around here, the clean theory is stable against disorder. So you get an easing transition here, C equal 1, Z equal 1. But if you approach the multicritical point, then there's something happening here. This blue line here is a theory that has finite randomness, not infinite randomness. So Z is finite here. Z from here to there is 1, and when it reaches here, it starts growing from 1 until it reaches the infinite randomness critical point, and Z goes to infinite. But this is finite disorder transition. This is gapless, critical, and has finite Z. Yes, there is actually a line of fixed point. This thing here is a line of fixed point. We did the strong disorder RG for that. We found this line of fixed points, but this is a different seminar. I'm not going to show that here. But you find that in our method as well. And that's what I'm going to show you. Okay, so the first experiments I come from here to there and these 3 lines here, and I see how is the dynamic exponent. This divergence is 1/2 delta, as the easing case. If I stay at the critical points here and there, I get the same tunnel exponent universality, psi 1/2. So the gap is vanishing exponentially fast with the system size, and these are these lines here. So this is double log here, and this is 1 log. If I put double log here and 1 log here, I get a straight line. So that's there. And you see I need to go to very large systems to really convince ourselves that it is a straight line. Then I go to this multi-critical point here, and again, I plot the log of the gap, divide by L to power a half, and I get a data collapse. The same thing here. Again, data collapse, a different function. As the function doesn't have to be universal, but this exponent is universal. So I do experiment coming here to the critical point here, but before reaching that critical point, I see that there is a mass gap, so there is no Griffiths phase around here. So the gap is finite. You see that it vanishes only when delta goes to 0. So this is from criticality is that direction. And it vanishes as in the easy universality class as expected, z equal 1 by CFT, so you get the delta proportional to the small delta, the distance from criticality. So if I do the experiment along the critical, the transition, along the transition, while you are far away from this multi-critical point, you get z equal 1, which is these two lines here. And then you enter the blue region, and z started growing. And it grows and diverges as you approach the multi-critical point. So that's the distance from the multi-critical point, and this is the z. So, okay, so then I come to my, time is up a long time ago, I don't know. Sorry for that. So I presented to you a method for compute the mass gap of free particle quantum systems, which are, I don't know, maybe, I don't see how you can compute that with computational effort less than proportional to L, right? So probably it is optimal. Of course, it's applicable to free particle between codes because there is no Jordan ring transformation, but there is a fermionic spectrum. It gives analytic prediction for us in the case of clean systems, so coming from the Laguerre bound. In the random transverse field is in chain, we recover known results as should be. If you want to put forward this method, and new results on the surface fields that are not understood analytically, and apply that for the random family model where you get a rich phase diagram with a clean finite disorder, infinite disorder criticalities, and Griffiths phase. With that, thank you for your attention. No, this has to be free fermionic. Many body localization is not free fermionic.
Then you cannot. It has to be free fermions always.
Yeah, I can tell you if I can put that in this form here of in this form like the Hamiltonian, then we are in game. But many body localization shouldn't be here, right? Because interactions are important there. But you can study Anderson localization if you wish with that.
Yeah,
Anderson localization is piece of cake here.
Yeah.
Hey, you have Hamiltonians parameterized in terms of N and P. P is the range of interaction somehow.
Yes, this
and there is this
P
parameter,
here.
yes, and there is this parameter omega. Is it possible to assemble these charges in terms of a transfer matrix and analyze these multitude of Hamiltonians in terms of inhomogeneities in the transfer matrix? I mean, I know the construction is totally different, but I was wondering if it would be possible to do something like that.
I don't think so, but I'm not sure. My first answer is no, but maybe I'm wrong. But I have to be more careful. My first answer is no, but don't take it for correct.
Thank you.
It seems like there's a lot more information in the roots of this polynomial than just the gap.
Yeah, the other roots are the remaining quasi energies, right?
Right. So I'm wondering whether you can use that to learn more about the.
Yeah. You can. I'm just extracting this one here, right? But from the polynomial, you can get the other ones, and we have done that, and then you can construct the entire spectrum, the low end spectrum at least. We have done that, yes. But yeah. With the low end spectrum, you can compute the specific heat, for instance, and yes, the low temperature specific heat.
This exponent Z of the gap controls some kind of observable. This is an ignorant question.
It is the ratio between the correlation length exponent and time length exponent. So this is Z. So correlation lengths exponents, you can measure that. For instance, if you get a magnetic system, you can get that from neutron scattering. dz, it appears in the specific heat because it's more or less it is proportional to gap. So in these theories here, Z appears directly in the specific heat. It also appears in the susceptibility with because you have the scaling relations, and specific heat is T to the Z. Susceptibility is 1 over T to minus Z, T to 1 minus 1 over Z, actually. And the specific heat is T to 1 over Z. Yes, but it is for the transverse field easing model. Other models can be something else. So yes, it can, it's not a direct measurement, but comes from the theory that specific heat and susceptibility are governed by Z.
Okay, more questions? No? Okay. We thank again José.
Thank you very much.